Hello folks, I hope everybody can see me and hear me. YouTube made some changes. I'm still catching up to see if I can understand what they're doing here. But anyways, I hope you can hear me fine. Anyways, welcome to Rational Science. Welcome to the end of the world, at least as we know it. You have to give me credit for that. Yeah, I've had a theory for now 20 years in which I say that man is soon to become extinct. Our species will wither away. In fact, not wither, it'll kind of go with a bang, okay? And one thing I want to say about that is that a lot of people introduce things into my theory which are not there, which I never said, okay? I want to clarify that. A lot of people talk about the rich and powerful, the Illuminati, maybe even the Jews or the Chinese taking over the world. That's not part of my theory, okay? Just want to clarify that. I'm not saying it doesn't happen. I'm not saying it does happen. I don't care if you believe or don't believe. All I'm saying is that's not part of the theory. The theory says that no matter what we do, whether we stand on our heads, no matter what anyone does on planet Earth, okay, we will become extinct, okay? There were, as far as I know, there were no Illuminati among the T-Rexes, okay? They died the same way we're going to die. We have to die in the same way they died. And if they had no Illuminati, then obviously Illuminati or rich people or powerful people play no specific role in the theory of extinction. Okay? And again, it means that we have to imitate whatever happened to the dinosaurs, the Permian synapsids, and so on. In other words, we're going to die in the same way all of them died. And how did they die? Well, their economics fell apart. Okay, their whole economic world fell apart. What does that mean? It means that, an animal also has economics. They don't have the economics that we're thinking of, money and interest rates and banking and all that stuff. No, they have a little different type of economics. The economics of a wild animal is food. That's what they manage. Management of resources, that's economics. That's what they manage. They manage food, okay? And, when the Triceratops stock market goes down, well, the T-Rexes suffer big losses, so to speak, okay? So that's what happened to them. And we're going to have the same situation, when our food runs out, then we're going to go extinct. Why will food run out? Because we manage all that through money, through this abstraction that we created. And the theory says that money will be no more. And there is no other theory on planet Earth like it. So whether you believe in it or not, at least you have to grant that it's a new theory. You won't hear it anywhere else. The theory is money will be no more. The global economic system that man created will fall apart when it does. Not if it does, but when it does, no one will have incentives to produce or distribute food to the cities. No intervention by Illuminati, no intervention by the Jews, no intervention by the Chinese or the Russians or none of that, okay? There is no provision for that in the theory. That's all I'm saying, okay? Okay, the other issue I wanted to talk about real quick or clarify is that a lot of the people who do not understand, I believe, that's the best word I can use, they don't understand the rope hypothesis, the thread theory is also known. They don't understand it because they harp on the wrong issue. And the issue is the word object. That's the key issue. That's why I'm saying the word object destroys all religions. What is the issue there? The issue is that these people are saying, okay, why can't I touch the rope? Why can't I see the rope? I mean, there's gazillions of ropes converging on an atom, okay? And there's gazillions of atoms. We can't see any of those ropes. Why not? Well, again, the definition of the word object is not that which you can see or touch. The definition of the word object is that which has shape the rope has shape, it meets the definition of the word object. So far so good, or are we having problems there? So anyone raising an issue of touch and see, why can't we see, why can't we touch? Well, I have to believe that has a mental problem, because I don't know how else to clarify to that person that the definition of object is not that which you can touch or see. And I've got a good example. I mean, we have gazillions of atoms and molecules of air hitting our eyes this very moment. They're there. There are gazillions of them, and we can't see a single one. And there we're talking about atoms and molecules. And here we're talking about something gazillions of times thinner, smaller, flatter, whatever. You're talking about something that is much thinner than the diameter of a hydrogen atom. And so you're asking to see something that you cannot see, that you cannot touch. Therefore, it is irrational for someone to raise the see-touch criteria first, and second, to say, let's go to the lab to see if you can demonstrate the existence of the ropes. These people are demented. They're what I call idiots. Okay, they don't have little ideas. They have big ideas, and so it's idiots. They're idiots. So yeah, anyone who talks about experiment, demonstrating, proving, presenting evidence, touching, seeing, using any of the senses, he's a mental retarded individual, because he can't follow a rational explanation, a rational mechanism that is proposed to him. And especially he can't follow definition. They give lip services to definition. They say, oh yeah, it's an object is that which you can touch, or which has shape. They conceded, but they don't know what they conceded. They sold their soul to the devil, and they don't realize it, because now they can't bring in the see-touch criteria. You can't say you're going to touch the rope. You can't say you're going to touch magnetism, the mediator of magnetism. You can't touch or see the mediator of gravity. And they say, well, if there's gazillions of rope, why can't I see it? Well, because that's not the criterion. The criterion for object is that which has shape. And Mother Nature specifically made the rope invisible, untouchable under any circumstance. And how do you get that thought to these people? So yeah, they have serious, I think it's mental problems, because they can't follow a rational explanation, and primarily because they don't pay attention to definitions. They're not consistent with their definition. They give lip service to them. Okay, last time we talked about time. And one of the things we found out is the mathemagicians have no idea what time is. Here we've had this word, at least since the days of the Greeks, because we had good old Aristotle, Ari as I call him. Aristotle, he talked about time, and he talked about in his work called physics, okay? And so we've had this word for a long time. And here we are 2,000 plus years later, and not a single mathematician on earth, from Cambridge all the way to Harvard, can define the word time. We had Stephen Hawking, his brief history of time of 1988, and you won't find it defined there. And you say, hold it, this guy's a physicist, so-called physicist, mathematical physicist. He's an expert on all these equations. He uses time in every equation that he writes, almost. And he doesn't know what time is. He can't define the word time. He even concedes that he doesn't know what time is. So we have a problem, because here we have all these mathematicians, and they say, look, I'm going to use time for this. I'm going to put seconds in my equation, but they don't know what time is. Now you figure that out. And just in case, they don't know any of those words. They don't know what a field is. They don't know what mass is. They don't know what point is. They don't know what a line is. None of the words that they use do they have a definition, a scientific definition for them. And so we don't know what they're talking about. But they claim through those definitions that they can interpret how this universe works for you. And when you say, well, how does this work? How does that work? They say, well, you got to study math. Okay, so that's the answer. You got to study math. If you didn't study math, you won't understand. Okay, so what did Airy do? Well, Airy, he did talk about time, and before he got to time, he started first with defining words such as continuous, what continuity meant to him, what infinity meant. Then he went into place, and then he went later on to time and to motion. Okay, so this is where he started, and that's where I'm going to take over from the other day. I'm going to just follow up, and here we have good old Airy. And first thing that they did, together with Euclid, who came a little later, right? They tried to define what an object is. Very loosely, they never gave any importance to this definition, which is the number one definition you have to have in physics. They didn't realize, first, the importance of that definition, and second, they had the right notion, but then they never used that notion for anything. Okay, and that's where the problem is. So Euclid said, what is an object, essentially? Okay, a boundary is that which is an extremity of anything. And what is a figure is that which is contained by any boundary or boundaries. So more or less they had the right idea, or Euclid had the right idea, that an object is that which has shape, which has something around it. We'll call it a surface, a perimeter, a boundary. Call it whatever you want. We get the idea. The idea was very close. If it's not right on the money, it's very close to it. Okay, and Airy had the same idea before him. I guess they got this from their ancestors as well. You know, it says bounded by a surface is the definition of body. I think it's straightforward, right? So these guys had this notion that a body, a thing, an entity, a substance, is that which has shape, which is the definition that we have in rational science. That which has shape. You want to call it surface, that which has surface, that which has perimeter and outline, fine, no problem. As long as we're on more or less on the same page, okay? Okay, so what is the problem with this? Well, they went on to the next word, or at least Aristotle did, and this is what he did. He says, he defined place, okay? So what is a place? Position or location. Well, Airy says, place is the boundary of the body which contains it. So he's saying that place is a boundary, and he just said that bounded, you know, a boundary belongs to a body. So essentially he's saying place is a body. He's treating location, in other words, you could say location or position, the site occupied by the tree. When you pull the tree out, that hole that he left behind, that's a standalone object according to Airy. It's got shape, it's got boundaries. And he continues, just to make sure you understood, in case you missed it, right? It says, place is this boundary itself, contains no extension over and above the bulk of the body which comes to be in it. Place is what contains that of which it is the place. Place is no part of the thing. Place can be left behind by the thing and is separable. Okay? So what is good old Airy telling us? Well, he's saying that place is a standalone object. Place has surface. Place has perimeter. When you remove the tree or the dog or the rock, you're leaving a hole behind that has the shape of whatever you pulled out. And the only way an object can exist if it occupies a place. But then it's like it's a hole waiting for it to be occupied. And of course, this hole changes shapes, because if you put a dog in that place and you replace him with a rock, well, a rock might have a little different shape than a dog or a tree, for that matter, right? And I guess shape changes its shape depending on the object that occupies it. That was his notion. Okay? So what the big problem here is that he's treating place as a physical object. And he doesn't realize that. And that's, again, because he didn't pay attention to what he defined. He defined object or substance or thing, body as he called it, as that which has a surface, that which has shape, that which has a perimeter. And then he applies that same definition to place, saying, oh, place also does have a boundary. So what are we going to learn here? We're going to have this concept called place, right? And this place is also going to have a boundary. It's going to be an object essentially by definition. Okay. Okay, from there he moves on to time. So what is time? Well, here we have an idea what notion he had of time. Okay, time is infinite. Time indeed and movement are infinite. So first thing he says, they're both infinite. Why? Because you can chop them into pieces and you can add more time to it. Either way. Okay, you also, in the case of motion, you can add more meters. And if you have 1 meter of length, you can chop that up into little pieces as much as you want. So in both directions, division and addition, it's infinite. Okay? So time is a measure of motion and of being moved. Motion always exists. Therefore, time exists. Okay, that was his reasoning. He says time is number, meaning, I guess the translation, I didn't like the translation very much because I don't know what number of motion means. I think he meant the amount of motion, okay? So time is amount of motion. That's as best as I can understand what he's saying there. Time is not movement, but only movement insofar as it admits enumeration. So as soon as you put numbers, according to area, right? As soon as you put numbers to motion, now you're dealing with time. And I don't know exactly what that really means because I can put meters to motion and that's not time. But I guess in his little mind, he thought he answered the question, okay? Okay, so what is motion? That's the subject of today. One of the subjects. The other one is the fact that we're going to have concepts that are going to be moved around. And that gets scary because you're going to need 10 beers to understand that, okay? So please go to your fridge, get your beers now, and suffer later, okay? And here it is, okay? Here we have Ari talking about motion, okay? It begins by defining. He says, to define the infinite, you must use quantity, okay? So you're going to deal with math here in order to talk about infinite or infinity, right? In your format, but not substance. You cannot use a body. You cannot talk about an infinite body, meaning extended body that is infinitely extended. He says you can't talk about that. You can only use the word infinite or infinity in the context of quantity. Okay? Okay, we have no problem with that. The mathematicians want to use the word infinite in terms of number lines. No problem. We have no problem with that. Keep it in your in your own doghouse. Don't bring it out here, okay? Don't bring it into physics, okay? Because physics deals with substance, with bodies, with things. And if you're going to talk about a number line, then the fact that you can add numbers to numbers and forever, or cut a number into all kinds of little pieces, well, that's fine in mathematics. Just don't bring it into physics because it's got nothing to do with the physical world that Mother Nature runs. She doesn't know math, okay? She only deals with objects, with bodies out there, everywhere really, but especially out there in the universe, okay? Motion is supposed to belong to the class of things. I love the fact that he treats motion as a thing. He uses this word. He's got to use a word. He's going to use the word thing. Is he saying that motion is a body? Is it standalone substance, thing, entity? So he uses the word thing, and that's part of the problem. I don't know if there could be something lost in the translation. Okay, we have to concede that there could be a problem there as well. I don't know Greek, so I can't tell you exactly what he said or what he meant. All I can go is with translation, and they use the word thing. Okay, so we use the word thing to refer to everything, like concepts and objects and everything. Now, in physics, we make a distinction. A concept and an object. Those are two different things, okay? Objects are things because they have shape. Concepts are just nouns that require, first of all, they don't have shape. But then every concept requires two objects. So it's a relation between two objects. Okay, that's important to know the distinction, to understand that distinction between concept and object. Every word in the dictionary can be put under one or the other category. Either it is an object or it's a concept. Either it has shape or it doesn't have shape. Either it's a standalone object, the only one in the universe that when you present it, you point to it, or it's a relation between two objects. Okay, so concepts and object, are separate. They're two different types of words. You can't mix them. And he's going to mix them. He's going to say that motion is some kind of thing. Bad wording. He should have said it's a verb, not a thing. But okay, let's continue. Which are continuous. And the infinite presents itself first in the continuous. In other words, he's going to relate infinity with continuity, with continuous, okay? What is infinitely divisible is continuous. And again, that was his notion of infinity, okay? That if you can chop it up into pieces, you got infinity. You can do it forever, okay? Chop something in half. As long as it's not a something, it's a number, and you can do whatever you want, right? Even location, maybe. I don't know. You could say that a concept you can chop up into as much as you want. And he called that potential infinity, right? That you can imagine, you can conceptualize dividing a number or a location as many times as you want. Okay, that was his notion. And he says, motion in its most general and primary sense is change of place, which we call locomotion. So what was the problem there? Well, the problem is this word change. See, change is already motion. There's no such thing as change without motion. So he's using a synonym because change is a synonym of the word motion. And here we have a definition of change, just in case. Okay, definition of change that you find today in the dictionary, because the dictionary still defines to this day motion. Everybody, in fact, does. All kinds of dictionaries, especially specialized dictionaries, they'll all define it the same way. They say, what is change? Change is to make different. And just look at the verbs. To make, to transform or convert, to substitute, to give and take, to transfer, to get, to remove and replace. All verbs. What is change? A verb. That's what it is for the purposes of physics. In ordinary speech, it's a noun. Not in physics. Physics, change means motion. And motion means change because they're synonym, and we have to define that word. And we can't say that motion is change. No, motion is two or more locations of an object. Now we can understand it because we didn't use any synonyms to define the word motion. Okay? So what is the definition that the good old mathemagicians today have, that they have inherited from Mr. Aristotle? And here you have a couple of them, okay? A couple of definitions. The first one I'd like to mention is position. Why? Because position, according to mathematics, okay, here's the definition, says a Euclidean vector. Vector is already motion. So position, which is a static concept, is defined in terms of a vector, which is a dynamic concept. Fine. That represents the position of a point P in space in relation to an arbitrary reference origin O. So what are we saying? We're saying that you put a stake in the ground, okay, and you draw two lines from there, okay, and we're going to make this Cartesian coordinates on the ground, right? And all that position is the number of steps that you need to find a treasure chest. Five steps this way, 10 steps that way, right? And you reach your treasure chest. So position is motion, according to the mathematician, because they're giving you instructions on how to get there. That's what position is from a mathematical point of view. So position is motion. What is motion? Motion is the change. Again, wrong word. Motion is the change in the position of an object over time. And I like the fact that they use the word time to define motion when you are supposed to define motion before you define time. Can you define time without motion? Obviously not. So again, it's circular because they put the word time to define the word motion. It should be the other way around. You should not need to use the word time to define the word motion. Motion needs to be defined before time. There's got to be an order in which you define terms in physics. You can't just define them in any old way and say, oh, I'm going to define exist before I define object or before I define location. It doesn't work that way. Okay? You have to define them in the proper order because you're going to build the definitions on simpler concepts, on more fundamental concepts. Okay? change, a difference in a state of affairs at different points in time. Again, change defined in terms of time. And so none of these people ever learn how to define words scientifically. That's why we have not one, no scientific definitions of any word in mathematical physics. Not one. Especially not one, the important ones. Maybe, I don't know, maybe the word house has a definition in mathematical physics. I don't know. But the point here is that they don't have any definitions of the important words that they're going to use. That's the first issue. The second one is that all of them contain motion. All the concepts used by mathematical physics are concepts, really. And they're all dynamic concepts. They all have motion embodied in them. And that's what I want to show next, okay? Okay, so what are these dynamic concepts? Well, here you have a series of words that the mathematicians use every day. These words are outlawed in science. They're outlawed in physics. First, because they're not defined. They're undefined terms. That's the first problem. The second problem is that they are concepts. And third is that these concepts are dynamic concepts. That means that you can't say that you're going to move a dynamic concept. Okay, and here I have an example so that you see where I'm going with all this. Okay, let's see if I can get it up here. Okay, here we have a kangaroo on the left. That's an object for the purpose of physics. The one on the right, the so-called jumping kangaroo, is not a kangaroo. And people don't understand that. That's not a kangaroo. That's called a jumping kangaroo. Jumping kangaroo is not a kangaroo. You can't say a jumping kangaroo moved the house or a jumping kangaroo jumped over the house. You can't say that in physics because the kangaroo's already jumping. What you have on the right is a dynamic concept already being qualified with an adverb, and jumping in this case is an adverb because it qualifies motion, just like swimming is an adverb, just like flying is an adverb. These are not nouns, they're not adjectives, they are adverbs, they qualify motion. And so again, the problem here is that all these words that these people use, let's see if I can get them back up here again, all these words are dynamic concepts. So you can't say you're going to transfer energy. You can't say you're going to move a mass. You're going to wave the wave or vibrate the wave or extend the field all the way to the edge of space-time. All those are irrational statements because they're already dynamic concepts. You can't stretch a dynamic concept. You have to identify what is the object. And if you don't identify the object, you're not doing physics, you're doing irrationality only. Okay, did I get my point across? Okay, I don't care if you agree with it or not, you better have a good reason for not agreeing. Okay, so let's go with the first one. Here's energy. Okay, so what is energy? Well, the first thing is, if you define a word, it's not an object. It can't be an object. In science, we do not define objects. In science, we point to objects. Okay, we point to them, name them, and someone then identifies the image that's in front of them with a word that you pronounce. So if you want to teach an ET your language, you say tree, and you point and say tree. And ET looks, he sees tree, standalone object, it's the only object in the universe, that thing that's in front of him, and it's called tree. Okay, that's how you present objects in physics. If you can't do it that way, it's not an object. Okay? Okay, so what happens? First thing is energy lacks a definition. Okay? There's no definition for it, and here we have testimony. We always need proof and evidence to convince and recruit, right? And so here we have Mr. Fineman. He says it is important to realize that in physics today we have no knowledge of what energy is. And so one of the biggest spirits of quantum mechanics is this famous word energy. It's been around at least since the days of Aristotle. No one has any idea what energy is. Okay, and then what's the next issue? The experts say that they have no idea what energy is, and then it says, yet mathemagicians say universe came from energy. the universe popped into existence from energy, specifically the breakup of positive and negative energy. And here we have testimony, again, proof, evidence for all those who want to be convinced and recruited and converted, etc. Okay, here's Mr. Hawking saying it in his book, A Brief History of Time. He says, at the Big Bang itself, the universe is thought to have had zero size. There are something like blah, 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 millions of, with 80 zeros after it, particles in the region of the universe that we can observe. Where did they all come from? Yeah, where did they? The answer is that in quantum theory, particles can be created out of energy. In the form of particle-antiparticle pairs. Okay, how energy became a particle, that's got to be an interesting mechanism that he can show us, okay, or he can explain to us, okay, not show us, but explain to us. But that just raises the question where the energy came from. Yeah, I guess from God. The answer is that the total energy of the universe is exactly zero. The matter in the universe is made out of positive energy. Now, twice zero is also zero. Thus, the universe can double the amount of positive matter energy and also double the negative gravitational energy without violation of the conservation of energy. And so they created this positive negative nonsense. I don't know if I represented it properly there. I have all these smoky, halo-y kind of things there. I hope that's what they're talking about, all that energy. And how they can tell the negative from the positive there, I don't know. Can you tell me why? Is it because one is blue and the other one's green or yellowish? I mean, you know, these people get away with murder because they use this word, this undefined word energy, which good old Richard Fineman says, you know, we have no definition for. And with this, they're going to use this undefined term, this idiotic word that we've had for 2,000 years that nobody knows what it is. And with that, they explain everything. And no kidding, I can do it with the word spirit as well, you know, or angel or whatever. I can do it with God. How's that? I mean, if you don't have to define that term, we don't know what energy is. And if you can define it, it makes it even worse because now you have a concept because objects we point to, then, you know, what is the mechanism that they propose? What is the mechanism of energy coming into the universe as a particle? How did it go from energy to particle? That's what we want to know. We want to know the mechanism. Don't give me any math. Don't tell me that, look, here we had positive energy and we're going to call this mass, the other one is negative, we're going to call it gravity or whatever. That's all nonsense. That's all verbiage. What we want to know is the mechanism. That's what we're interested in. We want to know how Mother Nature runs her shop. Okay, so the issue is mechanisms. And that's what we don't have from mathematical physics, from quantum or relativity or string theory for that matter. Okay, how about mass? Next word on the line. Here it is. Okay, what do we have? We have mass is defined, again, if you can define it, it's not an object. You have to be able to point to mass. If you can't point to mass because it doesn't have shape, because it's a concept, then yeah, it's a concept. It's not an object. Okay, it's not a standalone object. I can't bring to the conference mass. Say, look, I've got this. This is mass. I can't do that because mass is a number. It's a concept. Okay, what is it? Well, first of all, it lacks a definition. We have no idea what mass is, and here, yeah, we have proof, evidence, so that we can convert and recruit. Here it is. Okay, we have at least three testimonies. Here we have Edwin Taylor and John Wheeler. Nature does not offer us any concept as the amount of matter. History has struck down every proposal to define such a term. Even if we could count number of atoms or by any other counting method, try to evaluate amount of matter, that number would not equal mass. Okay, that's their opinion. Let's find out if we got more opinions there. Okay. Now we have in physical science, mathematics, right? One may distinguish conceptually between at least 7 different aspects of mass or 7 physical notions that involve the concept of mass. How's that for a definition? So we have no idea because there's 7 notions of mass. And then just in case the physics frequently asked questions, John Bias's site over there at Riverside says, when the particle is at rest, its relativistic mass has a minimum value called the rest mass, okay? As the particle is accelerated to ever higher speeds, its relativistic mass increases without limit. Okay, so what is good old Bias talking about? Well, he's talking about weight. See, one thing no mathematician, even since the days of Newton, has never been able to do is tell you the difference between mass and weight, because they are synonyms. And you say, Bill, you're crazy. What are you saying? We learned this in high school. We know mass is different than weight. No, there's no difference between mass and weight. And I'm going to prove it to you, okay? So, dear idiot, please open your ears, okay? If we take, we had the grand kilo, which is no longer the standard, but used to be the standard French kilo that was in Paris. We take that French, or let's do it even easier. Let's take a particle, right? A speck of dust, and it's got exactly consists of 1 million hydrogen atoms. How's that for a start? So we have a little speck of dust, and that speck of dust is exactly 1 million atoms of hydrogen. So far, so good? Okay, we take it from the equator to the North Pole. Its weight changed. Did its mass change? Well, people will say, a lot of them, people will say, well, no, its mass didn't change. What changes its weight? Well, how do you determine the mass of an object? Well, you weigh it. You put it on a scale and you weigh it. And you give it in terms of kilograms, which is the way you give weight. Kilograms. And so the question is, you're saying that its mass didn't change. What do you mean its mass did not change? Well, we still have 1 million atoms. Yeah, but you never defined mass in terms of quantity of matter, especially when you get to these relativistic masses where they say, oh, the speed changes the mass. If the speed changes the mass, we're talking about weight. And so these people are calling it mass. And what do they mean? They mean that it changed the number of atoms just because of its speed? What are we talking about? So this is the issue. The issue is they never defined the word mass scientifically in a way that you can use it consistently. And these people are saying that they tell you blah, blah, blah from their tongue out. Oh, mass is different than weight because this is quantity of matter. No, it ain't. So try again, okay? Until you have a definition of mass that we can apply there to this little grain of sand that consists of 1 million hydrogen atoms, and you take it somewhere else and you tell me that the mass didn't change but the weight did, then you tell me in that context what has changed in weight and what has not changed in mass. Is it the quantity of hydrogen atoms? So again, we have no definition, we have no difference between mass and weight until someone can figure out what the difference is. And then of course we have these other things, these other issues where you have the photon, and the photon is a so-called particle that has no mass. Then you have the black hole, the other end of the spectrum says infinite or density, it's got infinite mass and no volume, okay? And so you have it, if the rest mass of the photon were non-zero, the theory of quantum electrodynamics would be in trouble. Oh, so thank God that the photon has no rest mass, okay? And the black hole's radius is 0, which means its density is infinite. Yeah, we see these declarations, these statements every day in the literature. All nonsense, because here you have a massless particle, and you have a nothing, a zero-dimensional singularity, which has no length, width, or height, and it's got all the mass you want in the universe. It's infinite density. So what is it? Are these explanations valid for mechanisms? But, okay, so we have this black hole, which I talked about the other day, and here you have the good old mass, swinging a turtle around. You could replace that turtle with a star if you want. I don't care. The point is, how does mass do it? I want to know the physical mechanism. How is the turtle tied to that central mass that is a singularity, that is a black hole, and how does it compel the turtle to swing around it, to orbit it? So that's what they have to explain. I need a mechanism. Don't tell me math does it. That's mathematical gibberish. It has no place in physics. In physics, you got to give me a mechanism. Okay? You got to tell me what's in contact with the skin of the turtle. That's what I need to figure out. And yeah, for that they invented two words. One is wave and the other one is field. Let's get to those. Okay, so here we have the wave. Okay, what is the wave? Is this a physical object, standalone object? Can you bring me a wave and put it in the center of the conference room? No. First, if you can define it, then it's not an object. Okay, you got to point to it. Second, wave is a verb. Wave is what something does, and it's the something that you need to identify. And in the case of wave, it's usually particles which are vibrating. So don't talk about the wave, talk about the particles. Why talk about the wave? What is it that's waving? Well, they say electrons are waves. I thought it was a particle. Well, they say it's both. Whenever we need the wave, we bring the wave. Whenever we need the particle, we bring the particle. Whatever suits our theory best. You know, you're going to do the Compton or photoelectric effect, well, then you bring the particle. If you're going to do the photoelectric effect or the slit experiment or maybe polarization, well, then you bring the wave. Oh, that's handy. You just change in the middle. You change horses in the middle of the race, right? That's so nice, so handy, so ad hoc. Okay. Okay, so electrons are waves. There are waves of gravity. Okay, and this again, I'm going to present evidence, proof, so that we have conversion here. We have recruitment. Okay, here it is. Yeah, so let's just go through them one by one. Electrons exhibit properties of both particles and waves. Okay, so electrons are waves as well. Double slit experiment shows the wave aspect of the electron. Okay, gravitational waves are ripples in space-time. These cosmic ripples travel at the speed of light, carrying with them information. How do you carry information? I mean, on a knapsack or what? And then we have the other one, is light a waving of nothing? Yeah, if light is a wave, then what is doing the waving? And the physicist at the Ask the Physicist answers. In short, nothing. Nothing is a wave itself isn't made of anything. It's just a propagation motion through a material. Propagation of what? What is moving? I thought motion involved a physical object. These people say that there's nothing that is moving. Okay? And just in case, we have the last one, light travels as a wave. Yeah, light travels as a wave. It does not need any matter or material to carry its energy along. Carry its energy. How do you carry energy? I mean, on your back, piggyback somehow? I don't know how they carry energy. See, they use these words, and, when you criticize it, they say, oh, Bill, you're doing semantics. No, the guy doing semantics is the guy who tries to hoodwink you into thinking that that they can carry information, they can carry energy, they can carry a force, move a mass, bend time. That's the person doing semantics. Okay? If you're going to do a physical interpretation, if you're going to do a mechanism, you need to put objects there. You can't put a dynamic concept. Can't put a concept to begin with, but to put a dynamic concept makes it even worse. It means you don't even know the basics of science. Okay? Okay, and then we get to the famous word field. Oh, I love field. Field is my favorite word. Okay, here it is. Okay, what is a field? If defined again, if you can define the word field, it's because it's not an object. Okay, you should be able to point to a field, whatever a field is, and it better have shape. You got to make it visible. I need to see it. Okay, doesn't mean that you take me to the lab. No, I don't want to see it in the lab. I want to see it on paper. I want you to draw it on the board. I want you to use crayons and show the little baby or the kid and the toddler in kindergarten what a field is. I want you to draw it. If it's got shape, you better be able to sketch it more or less. Okay, so that you can point to it and say that's a field. Okay, is it a standalone object? Well, let's find out. Particle is an excited field, and here I've got a little GIF showing that. Let's see if I can get it here. I think it's this one. No, it's not. Well, here's the. I'll show it in a second, but here's the definitions that they have out there. What is a field? A physical quantity. So what's a quantity? What do we do with quantity? I mean, are you going to shake the quantity up and down, the numbers? That has a value for each point in space-time. So what the hell is that? Is that a field? Just a quantity or a bunch of values around space-time, around a center point, maybe extending radially ever weaker as it gets away from the center point? Is that what it is? That's not a physical object. That's in fact mereology. You're telling me what something is made of, first of all, but it's not even that good because you're telling me it's made out of a bunch of numbers, a bunch of quantities, a bunch of amounts. What the hell is that? You know, I want to see that monster. Can you bring it to the conference room? There are no particles. There are only fields, okay? At every point in space, there's dozens of little vibrating fields. What do you mean? How can quantities vibrate? Okay, and in front of you. But quantum mechanics says that when you look at the field closely enough, they resolve into individual particles. So what you have is a bunch of vibrating numbers, amounts, quantities, numbers, and when you look at them closely enough, he says close enough, then you resolve into particles. That's what, and this guy's a PhD, supposedly. I don't know where he got his, maybe at a monastery, you know. And then the last one, a point charge is space. In the space, its field will extend to infinity. So we have this so-called field, and it not only vibrates locally and turns into a particle, but it extends to infinity, okay? And so, yeah, when we look at some of the claims that were made in the past, in other words, some of the definitions that people made, especially people like Maxwell and what's his name, Faraday. Here I have their testimony. They speak from the tomb, from under the ground, and here it is, okay? Maxwell saw a field, the space in the neighborhood of the electric and magnetic bodies. In that space, there is matter in motion. Matter in motion. That's what a field is. And you got to identify what that matter is. Something is vibrating, something is moving there. You got to identify what that something is. And Faraday said, I cannot conceive curved lines of force, speaking about magnetism, right? Without the conditions of a physical existence in that intermediate space. And he studied magnetism and electricity in quite a bit of detail. So even though he was not a very learned guy in the sense he didn't have a PhD, but he had a practical understanding of magnets. He dealt with them a lot. And he said, look, I reached a conclusion that those lines of force that the idiots of mathematics today say, well, they're abstract, they're not real, we just use them to explain. No, he says, that's real. That little line of force, that's real. And Maxwell tells you the same thing. He says, look, there's matter in motion. It's those lines of force which are moving around. You know, the threads, because that's what they look like, exactly like that. And you say, well, Bill, how do you know all that stuff? I mean, we don't see them, we can't tell. Well, here, you see it here, okay? Here you see it. Here's a magnet pulling underwater, pulling one iron filing at a time. One iron filing at a time, because there's matter in motion sweeping around that magnet and pulling each one of those iron filings towards the magnet. And, you know, when you let it sit, you find all those lines of force on which the iron filings sit. And, yeah, when you do that, you know, what are you staring at? You're staring at a bunch of threads just going through the iron filings and keeping them there. That's what those lines of force are. Those lines of force are real. That's why they're called lines of force, because that force is something that you can feel, not with your hands, but by putting something that is subject to that force. Okay? And anyone who knows a little bit about inductance knows that the force goes right through the coil, and you put something there and moves it. So what moved it? You can't say the field moved it, because a field is not a physical object. Field is an abstract concept that is a dynamic concept made of lines of force. But you have to identify what those lines of force are. And we identify them as threads which are sweeping around the magnet, and now we can see why they pick up, the iron filings, because they're a physical entity which the iron filing detects, not you with your finger. So you're not going to show it by going to the lab and say, let me touch that magnetic field. No, you won't be able to touch the field or the lines of force, because Mother Nature specifically made them invisible and intangible. Okay, but people insist on doing experiments because they learned the scientific method from the mathematical physicists, and they think that's science. No, that's not science. In science, we do not move concepts, and we do not go to the lab to figure out what mediator we have for light, what mediator we have for gravity, and what mediator we have for a magnetic field or lines of force. No, you got to sit back, drink a couple beers, and visualize. Try to imagine what could be moving those iron filings. And if it's matter in motion, as Mr. Maxwell tells us, and if they look like iron lines of force, as Faraday said, which are real, it's very simple. What you have is threads moving around. And all you got to do is figure out how Mother Nature does that trick. And, in my book, the one that I put out the other day, The Rope Hypothesis, you'll find it in the description there. We tell you how that's done with threads. Do you believe it? We don't care. In science, we do not believe. It's in religion where we believe. In science, we explain so that someone understands. Period. That's where science ends. What continues is religion, belief, opinion. Okay? So we don't care about your opinions here. Okay, and then we get the charge. Let's see if I can get it up here. Got so many of these sometimes. Okay, so what do they say about charge? Well, charge is another word that completely misused, because, again, it's like a field. It's a number. And people don't realize it. No, it's a thing. They always think it's a ball. Charge, it's the electron ball, right? Even though the electron is also a wave. But that's beside the point. But what is charge? Charge is the value of an electron, of mathematical value. And they say, oh, we moved the charge. No, you couldn't move a charge. Maybe you moved an electron ball. We can accept that if the electron is a ball, but you can't say you moved a charge. You can't say you're gonna move the 10 tons. No, you moved the elephant, not the 10 tons. If you want to do a physical interpretation, if you want to give a mechanism, you got to put the elephant back. You can't say, well, I'm going to move 10 tons. No, that's what the elephant weighed. You can't say you're going to move his weight. You're going to move the elephant in physics, not the 10 tons. People don't understand that. Okay, and this is very important, of course. And let me tell you why. You can't put elephant in your equation. If you put elephant in there, people say, well, what is that? Is the letter E a variable, a constant? What is that, elephant? No. They have to put 10 tons because they can deal with that. They can't put an elephant in the equation up beside it'll probably flatten the equation out, okay? So if it's defined, it's not an object, period. So it's got to be, so if it's a physical object, you just got to point to it. And what is a charge? Can you point to a charge? Can you tell me what it looks like? Is it a little ball, is it a circle? Is it two-dimensional, three-dimensional? You got to point to it. If you can't point to it, if you got to define it, automatically it's not an object. It's concepts we define, objects which we point to. And you got to keep that straight. If you don't keep that straight, you're an irrational individual. That's period. We're done. There's not much more to say about that. And we have a definition for irrationality. I'm not going to deal with that right now, but if you look up, you'll find a video of mine that talks about that. Anyways, what is charge? It's 1.6 times 10 to the minus 19 coulombs. What is a coulomb? Not important. A unit. Some kind of unit. It's a number. That's what it is. That's what charge is. It's a number. Okay, assigned to the electron and proton for that matter. But typically used in the context of electrons, negative charge, they call it. Okay. No standalone object is called charge. You can't bring a standalone charge and bring it to the conference room. And no positive or negative in physics. We don't use this positive and negative energy, positive and negative charge, not in physics, or positive and negative poles of a magnet. Positive and negative just mean opposite. That's all positive and negative mean. The mathemagicians have no idea what positive and negative mean in physical terms. Mechanisms? So what if a magnet is negative here and positive there? You can't just say, well, how does a magnet attract another one? Well, positive attracts negative. So what did you say? You said X attracts Y? Is that what you said? You said black attracts white? What are you saying? No, we need to see a mechanism. If you don't have a mechanism, you haven't explained how this universe works. That's what we want to understand. We want to know how Mother Nature does her daily stuff, how she runs her shop. So you got to tell me how Mother Nature does gravity, how she does light, how she does magnetism, how she does electricity, how she manages the workings of an atom. That's what you got to tell me, the mechanism. If you can't tell me the mechanism, all you got is a mathematical description. That's worthless in physics. That's okay in religion of math, description. We need a little more than that. We need an explanation for how Mother Nature does her mechanisms. And charge doesn't help us in that regard because charge is just a number. Field is just a number. Energy is just a number. Mass is just a number. They're all numbers with units. We can't do anything with that. We can't say that, so many ergs of energy cause the wall to fall. We can't do that. Not in, you got to identify the physical object that came in contact with a wall. That's how we do it in physics. And that's where we separate the mathematical physicists, so-called physicists, with true, genuine physicists, okay? Okay, with that, I will see you on Wednesday. And today's Wednesday. What am I saying? No, it's, I'll see you on Wednesday, okay? And we're going to continue with this line of battering of mathematical physics. I hope you tune in. And if you're a mathematical physicist, I hope you have second thoughts about your religion. We'll see you then. Bye-bye.